Hi guys. Okay, so let's look at the double displacement reactions. What are double displacement reactions? We see them very commonly in nature. They are found under the oceans as coral reefs. They are found in the caves as stalactites and stalagmites. And we also see them inside our body. If we are not eating right, they can form stones inside the kidneys. Besides that, they are commonly used in the industry to create some specialty chemicals for us, and they are also used in the chemical analysis techniques to form the spot analysis. Okay, so in this video, we are going to be looking at the double displacement reaction. We are going to look at the products that are formed when two ionic compounds interact, and what kind of compounds are those? Are those soluble or those insoluble? And then we are going to be looking at the balancing of the equation, writing the total ionic equation, writing the net ionic equation, and identifying the spectator ions. Okay, so let's get started. Okay, so these are very beautiful pictures of coral reefs. And in fact, this is the double displacement reaction happening in nature right under the oceans. These beautiful colors of coral reefs come from the ionic compounds, which have a very specific color. Okay, so that is the coral reefs. And now let us look at the pictures inside the caves of the stalactites and the stalagmites. So this phenomenon again is a double displacement reaction where you will see the formation of these beautiful structures inside the caves. Okay. All right, now let's get started on our double displacement reactions. This is a general scheme of writing a double displacement reaction in which two ionic compounds that are soluble in water interact. Okay, so the cation of one of the ionic compounds combines with the anion of the other ionic compound. So we have shown this as outer and outer ions are interacting and making a new compound, which is a product. Similarly, the cation of one ionic compound then attaches to the cation of one attaches to the anion of the other to give you the next product. So that's the inner and inner. So this way you will see that the ionic compounds, when they dissolve in water, they ionize and they switch places. So these type of reactions are called the double displacement. So everybody gets to form a new type of combination. And so in this problem we are going to identify now is what are the products formed, what is the solubility of those products. Then we will look at balancing the equations, total ionic, and the net ionic. Before even we start, we need to do a little review on the solubility in water. Okay, so we have seen that from the previous video that the solubility rules, there are certain ionic compounds that are going to be soluble in water, and some of them are not going to be soluble in water. The ones that are soluble in water, we show them as AQ. Sorry, we show them as AQ. Soluble in water is AQ, and the ones that are insoluble in water are going to be shown as S. Okay, the ones that are insoluble in water are shown as S, and that is solid, and this is the precipitate. Okay, this is the precipitate, and this is found suspended. The insoluble ones are found suspended in the solution, or you will see them sitting in the solution, or you're going to see them floating on the solution. So anyway, so soluble, this is the rule of the solubility one more time, that all group 1A elements are going to be, all that form cations, all group 1A cations are going to be soluble in water. All nitrates, chlorides, bicarbonates, acetates are going to be soluble in water. All halides, chlorides, bromide, iodides are soluble in water, except silver, lead, and mercury, chloride, bromides, and iodides. And then all sulfates are soluble in water, except silver, barium, calcium, lead, and strontium. Insoluble in water are the carbonates of all the elements, carbonates, chromates, phosphates, sulfides, and hydroxides. But the exceptions to this rule is the group 1A. Anytime group 1A attaches to any one of these anions shown on the left-hand side or ammonium, then insoluble. then that is going to be soluble, sorry, but the rest of them are going to be insoluble. Barium, on the other hand, when it combines with the hydroxide, it is going to form a soluble compound. And group 1A hydroxides are soluble, ammonium hydroxide is soluble, so the ones that are insoluble are all other cations except the group 1A. Okay, next is we should know when we are doing the double displacement reaction is the charges. So again, this is a quick review on the charges. Group 1A plus 1 charge, group 2A plus 2 charge, group 3A plus 3 charge, 4A can form plus 4 minus 4, and it also can form sharing of the electrons, which is not going to be a charged species. So in that case, we will have metals, non-metals, and we will have the metalloids in group 4A that is going to form variable situations with their valence electrons. Okay, next comes the non-metals. They are in group 5A, 6A, 7, and 8A. Now, in very specialized conditions, yes, you can make them, you know, make like the noble gases. For example, xenon can be forced into certain situations and it can make bonds. However, general trend is that all noble gases or group 8A will not make any bond, whereas group 7A, 6A, and 5A are going to make -1, will have -1 charge, -2 charge, and -3 charge. Okay, and so they are going to be forming bonds accordingly. Now let us look at one example. We are given potassium iodide and it is combining with lead and nitrate. So we need to write down the ionic, net ionic, and the spectator ion. Okay, so potassium iodide. Potassium iodide is the formula Ki. Okay, and this Ki, when it combines with lead nitrate, and so this is the lead 2 nitrate. So this is going to be PbNO3 whole twice. And now predict the product. So based on that initial, the scheme, so outer and inner. So potassium is going to combine with nitrate and lead is going to combine with iodine. And so we are going to get our product, potassium nitrate and lead, potassium nitrate and lead iodide, PbI2. Okay, so next is identify the solubility, and the solubility is for potassium iodide. Potassium iodide is soluble in water, group 1A. All iodides are soluble in water except lead. So we have these rules here. So except the lead, iodide and silver iodide, but all iodides are soluble in water. So therefore, and then moreover, this is group 1A cation. So potassium is going to be dissolving in water. So we will write it as AQ. Lead nitrate, all nitrates are soluble in water. Therefore, it is also AQ. Potassium nitrate, again, is going to be soluble in water. All nitrates, and specifically potassium, which is a group 1A, highly soluble in water. Iodides are all soluble in water except lead iodide and silver iodide. Okay, so this is going to be as a solid. This is the precipitate. Okay, now remember that this AQ applies to potassium and this potassium ion, and it applies to the iodide ion. So before we start the ionizing, let's look at the balancing first of all. So let's look at the balancing. So here we have potassium is 1, iodine is 1, we have lead which is equal to 1, and we have nitrates. There are, and I'm not putting any charges here yet, but when we are trying to ionize, then we will nitrate it. So the nitrates are 2. Okay, so here we have potassium equal to 1. We have nitrate, sorry, the nitrate is equal to, we have a nitrate which is equal to 1 nitrate. And here, do not ionize a precipitate, but right now we are not ionizing. So just for the sake of writing, so we have lead. That is why I'm not putting the charges. Okay, so lead is 1 and iodine is 2. So let us look at what is balanced and what is not. So we see that the potassium is 1 and potassium is 1. Okay, and then we see iodine is 1 here, but iodine is 2 here. So clearly iodine is not balanced. All right, then we have lead as 1 here. We have lead as 1 here. Lead is balanced, but nitrate is 2 here and nitrate is 1 here. So that's also not balanced. So nitrates are not balanced and iodides are not balanced. So what are you going to do? You're going to balance the iodine. So if you put 2 here, this 2 applies to potassium and this 2 applies to iodine. So yeah, fine. It balances the iodine, but it messes up the potassium now. So we will have to change the potassium to 2 also here. So here you're going to put 2. So this 2 is going to apply to potassium, and now it is also going to apply to nitrate. Okay, so now what do we have here? So we just balance this out. So let's look at it now. Potassium is 2 on one side, and potassium is 2 on the other side. Okay, you have iodine as 2 on the reactant side, and you have iodine as 2 on the product side, balanced. Then you have the nitrate is balanced on the reactant side as well as on the product side, both the sides it's 2, and lead is 1 on both the sides. So this balances this equation. Okay, so that's the balanced molecular equation. Now let's write down the ionic equation. Now, ionic equation, detailed oriented, and in a way you already know it by now, but sometimes those details can overwhelm the students. Now, what is that? So this means that there are, now let's write down the ion. There are 2 potassium ions. Potassium is in group 1A. It has a +1 charge and it is aqueous. Okay. Next is there are 2 iodines. So the same thing that you do in the molecular equation, you put that in the ionic equation. The only thing you are now putting is charges. Okay. So iodine, group 7A, -1 charge, aqueous, soluble in water. Then you have lead. Okay, there is 1 lead and the charge is +2 and it is soluble in water. Then there are 2 nitrates which are again aqueous and soluble in water. Okay, so this is what we get from that. Now you're going to write down the product side. So there are 2 potassiums +1 charge each, aqueous, plus there are 2 nitrates and negative charge on each, aqueous, plus now PbI2 do not ionize. This is PbI2. PbI2 is not going to ionize because it is a precipitate. And if it is a precipitate, it is a solid, it is going to be suspended. So this one, I'm going to very specifically write that do not ionize a precipitate, never, because this is a precipitate, it's a solid, and it's just suspended in the solution. So now let's look at it. So we have 2 potassiums on either side, and both of them are aqueous. We have 2 iodines on, we have 2 iodines that are showing the change of state. So this iodine right here is going from aqueous to a solid state. So this is changing state. Lead is going from an aqueous state to a solid state. Okay, but the 2 nitrates on both the sides are aqueous. So what does this mean? This means that 2 potassiums +1 charge each, aqueous, and 2 nitrates on both the sides, negative charge, aqueous, are going to give you, they are not changing the state. In other words, they are the same on both the sides. So not changing the state. And this is these are the spectator ions. Spectator, T-A-T-O-R, spectator ions. So these spectator ions basically just watch the show. In other words, it's hard to identify whether the potassium is of a reactant or is it from a product side. Same story with the nitrate. However, what is our the net ionic equation? In the net ionic equations, you are going to write down net ionic equations. You write down those ions that showed the change in phase. And that one was which one? Lead, going from +2 aqueous state to, and combining with iodine, 2 iodine ions in the aqueous state to make PbI2, which is a solid. That is the precipitate. Okay, so here's the thing where students find it very overwhelming because there are so many details here. You have to write down the aqueous, you have to write down the charges, you have to write the balance states and so forth. So it's just not to worry, just focus on writing the molecular equation first. Balancing should be right, writing the formula should be right. If you know how to write the formula, then you know what the charges are, and that's all you need to put. So just make sure that anytime you are writing, for example, just a little review here. For example, if you have two FeOH, let's say, whole thrice, what does this mean? This means that this 2 applies to iron and this 2 applies to the hydroxide as well. This 3 applies to hydroxide. So this is going to give you 2 of irons, and iron is in +3 state, +3 charges, and 2 times 3, and that is going to be 6 OH ions. So pay attention to this thing. Okay. Similarly, if you have something like if you have let us say like 3 NH4 whole thrice phosphate. Okay, let's say you have this thing. So what does this mean? This clearly means that this 3 applies to ammonium and this 3 applies to all of the phosphate. Okay, so main thing here is, and I think that's going to make your life easier, is do not break up the polyatomic ions. Leave them together. Okay, don't break them up. And then, so this 3 applies to ammoniums. So how many ammoniums are there? This is from the 3. This also factors in. And there's only 1 phosphate. So for number 1, we do not put those in brackets and we don't write down there, you know, that this is 1. But here you have 3 times 3 ammoniums. So that is 9 ammoniums are present here, and charges +1. And you have 3 times 1, that is 3 phosphates are present here, and the charge is -3. All right. So another last little bit, another review here is that if you have, for example, here, ammonium, let us change, this is, let's make it ammonium 2 sulfate. What is the meaning? How do we get this 2, ammonium 2 sulfate? Where is that 2 coming from? This 2 is actually coming from on top of the sulfate. In other words, this is the charge on the sulfate, and we don't see any charge here. It's just 1. That means it's that for 1 we don't write it. So this means that this has ammonium is +1 charge, okay, and then sulfate is -2 charge, okay, +1 charge and -2 charge. When they crisscross, then we see that this charge comes here and this comes here. So that's writing the formulas. So this is just a review, and I'm assuming by now you know how to write the formulas, but just in case, you know, you are still confused, then this is where it comes from. Okay, so I'm just hoping that it was easy, and thank you for watching. Bye-bye.